Hello everybody, how is it going? Welcome back to my channel or welcome to my channel. This is Prodigious Mind, and in this video we are going to be discussing RSA algorithm. We will discuss everything about it that will help you understand the working mechanism of this encryption algorithm, whether it is Euler's theorem or calculation of public and private keys. In few words, we are going to discuss everything about how does keys work or calculated, how encryption and decryption works, and other concept it is based on. Basically all the details about RSA and the working of internal correlating components of it. Please watch the complete video for better comprehension. Also, later in this video we are going to see the basic implementation of RSA algorithm in Python. Before moving any further, I would like to thank each and every subscriber and viewer for supporting this channel. If you haven't subscribed to this channel yet, please consider to do so if you like, and do not forget to turn on the notification by tapping on the bell icon. Timestamps and all the resources shared in this video can be found in the description box below. The link to the tool we are going to use in this video is also in the description box below. Now let's just get started. RSA, shorts for Rivest-Shamir Edelman algorithm. It was publicly introduced in 1977 by three scientists named Ron Rivest, Adi Shamir, and Leonard Edelman. Hence the acronym RSA, which comes from the last names of these scientists. It is an asymmetric cryptographic algorithm, also known as public key cryptography algorithm. There are different variants of RSA algorithm. However, in this video we are going to cover the main route on which this encryption works or depends on. If you don't know the difference between symmetric and asymmetric cryptography, I have included the link to the other video that explains it in a simpler manner. But anyways, just for your ease, we will discuss it briefly in this video as well. So RSA algorithm is mainly based on primality, coprime, or in more technical and complex terms, Euler's theorem or Euler's Totient function. Let's first discuss the most basic difference between symmetric and asymmetric key algorithms. Then we will see its working mechanism. So as the name suggests, in symmetric key cryptography or private key cryptography, there is only one key used for both operations, i.e. encryption process and decryption process. In order to work both encryption and decryption, a secret key must be known to both parties prior to the communication who wants to communicate to each other. Let's suppose you and me. If we both want to communicate over an encrypted channel using symmetric key encryption technique, then we both need to have a secret key. So the plaintext encrypted by you can be decrypted at my end, and the plaintext which I encrypted at my end can be decrypted at your end. The result or outcome of encryption gives ciphertext, which is in simple words the encrypted form of the plaintext. I believe you understand the concept of symmetric key cryptography. Let's assure that by looking at this pictorial representation. Now, on the other hand, we have asymmetric key algorithm. Let's suppose there are two parties involved who wants to communicate over an encrypted channel using asymmetric key encryption technique. Now, in this scenario, unlike symmetric key encryption, no one is forced to share a secret key. That's because there is a whole different concept of keys. Instead of one key used for both operations, which are encryption and decryption, there are a pair or set of two mathematically related keys possessed by each party or entity, known as public key and private key. I will have two keys, one is private and the other one is public, and it goes same for you. You will have your own private and public keys. If I encrypt a text using your public key, then you would need your private key to decrypt it. And if you encrypt a text using my public key, then I would need my private key in order to decrypt the ciphertext encrypted using my public key by you. So more security in terms of key sharing mechanism. However, there is one thing to note here. Both encryption and decryption operation can be performed using either keys. The only twist is a same key cannot be used for both operations. One can encrypt a plaintext using either his or her public or private key, but in order to decrypt it, they have to use another key that was not used earlier to compute the ciphertext or during the encryption process. The difference between private key and public key is that private key is supposed to be a secret and private to the user, hence its name, and that's why in common scenarios public key is used in encryption and private key is used in decryption in order to maximize the confidentiality, as private keys are supposed to be secret to the owner only. On the other hand, public keys can be shared with anyone else. These two keys may seem like different to each other, but they are mathematically linked to each other, and this is why either of key can be used for anyone one operation and the other one for the next operation. Don't worry, we will see how these two keys are related to each other in terms of mathematical relation in a few moments later in this video. If you have any difficulty understanding this, let's have a look at this representation here. Now I believe you understand the basic difference between these two types of cryptography. So RSA is an algorithm that is an asymmetric encryption technique. There are two keys, one for encrypt and second for decrypt, known as public key and private key. The key size is 2048 to 4096 bits. However, there is 512-bit key size also, but for obvious reasons, it is not secure and can be cracked easily. As we discussed earlier, the RSA algorithm is based on few concepts such as primality, factorization, etc. Let's discuss few important concepts that it is based upon, and we will discuss other stuff along with that as well. Let's start from the basics, shall we? So what is a prime number? So a prime number is a number which cannot be divided by any other number except 1 and itself. The smallest prime number is 2, and then 3, 5, 7, 11, 13, and so on. You get the idea, right? If I want to put it in coding terms, then it is something like this, where any number is any other number except 1 or the number itself. We will also discuss a simple Python script to find all that in a moment. Just for now, focus on the theoretical learning aspect of this video. Now the second concept is coprimality, or what are coprime numbers. If there are two numbers, let's say x and y, and the GCD or greatest common divisor of xy is equal to 1, then these two numbers are said to be coprime or relatively prime to each other. In plain English, if both x and y do not have any common divisor, then they are said to be coprime to each other. Please note, if two numbers are coprime to each other, then it is not any condition that both of them has to be prime numbers. For example, 5 and 4 are coprime, as both of them has no common divisor except 1, hence GCD is equals to 1. So coprime numbers are a set of numbers whose GCD is equal to 1 or do not have any common divisor other than 1. Now we understand the basic stuff. Let's get to a level higher and discuss Euler's theorem. So Euler's theorem states that if there are two coprime numbers, let's say x and y, which simply means the GCD of them being 1, then they can be represented in this below mentioned form. Don't mind the symbol in exponential power, we will see what does it mean later. For now, just note that mod here is the same mod operator we use in programming, which represents the remainder result, and a is any integer. Let's execute a simple command to check whether it is right or not by taking two coprime numbers. As you can see, no matter how many times we multiply or increase the power, the remainder we get is always 1. Euler's Totient function. In the equation we discussed earlier, we seen a symbol there. The symbol is known as phi, a Greek letter which represents Euler's Totient function. So what is Euler's Totient function? Euler Totient function denoted by phi represents the count of total positive numbers that are mutually coprime to a number n, where n is any positive number greater or equal to 1. For example, if we want to find Euler's Totient function for number 9, then we will have 1, 2, 4, 5, 7, 8. So there are total 6 numbers less than 9 which are relatively coprime to the number 9. This 6 here is nothing but the Euler's Totient function of number 9. Simple, isn't it? Let's take one more example. What if we want to find Euler Totient function of number 37? Not so simple now. Or what about 613? Now that's a problem, isn't it? Don't worry, we have a way out of this misery. Let's put case 1 tag on this. So according to the same theorem, if a number n is a prime number, then in order to calculate its Euler Totient function, all we need to do is -1 from it. For 37, the Euler Totient function is 36, as 36 is a prime number, and for 1613 we have 612, as 613 is also a prime number. Now let's see case 2. If there is a number n which is not a prime number, then the Euler's Totient function for this number still can be computed easily if the product of two prime numbers is equal to the number n. In simple words, let's suppose there are two prime numbers x and y and the product of x and y is n. In this scenario, the Euler's Totient function will be x minus 1 multiply y minus 1, according to the case 1 we discussed earlier. Let's discuss one more concept, then we will see a Python script to compute everything we have discussed so far. Modular Multiplicative Inverse. Let me explain this to you in a very simple words. If there is a prime number n and there is another number x where x is not divisible by n, which simply means the remainder of x mod n operation is not equal to 0, then it can be expressed as this form. In other expression, we can put it in this form, which simply means this. Here the y is the modular multiplicative inverse of x and x is the modular multiplicative inverse of y. Now let's take an example. Now what if n is not a prime number? So in this case, if x and n are co-prime numbers, then modular multiplicative inverse can also be calculated using the last discussed equation, which is this. So let's have a look at this Python script now. So here are a bunch of functions for calculating Euler's Totient function. Each function has its own work and works depending on the type of case, such as finding Euler's Totient function if a number is a prime number, or if product of two prime number is equals to that number, or even if neither of these cases matches, it will still give us the Euler's Totient function if there is any. Let's have some examples, and then we will move further towards the implementation of RSA using the knowledge we have acquired so far. Let's understand RSA algorithm step by step. So the first step is to choose two large prime numbers. Just for the sake of simplicity and ease in understanding, we will choose not so large numbers because this will complicate the learning and understanding level. After choosing the two prime numbers which are p and q, let's say 97 and 53, step 2 is about calculating the product of p and q, which is n. So the product of p and q is 5141. In step 3, we need to find the Euler's Totient function. Earlier, we discussed that we can calculate Euler's Totient function easily if the product of two prime numbers is equal to the number n. In this scenario, it just fits right in because initially we have chosen two prime numbers as it was also required. So the Euler's Totient function for n will be the product of p minus 1 and q minus 1. The Euler's Totient function, or phi n, will be 4992. Once we calculate the phi n, the next step is to choose a derived integer such that it should be greater than 1 and less than phi n. Also, it should be co-prime to phi n, which means the GCD of phi n and integer e must be 1. Let's take e as 2053. Step 5 is all about public key exponent. Here e is known as encryption exponent and combined with value n, it will be our public key. In step 6, we need to compute d, which is decryption exponent. In order to compute d, we can express this modular multiplicative inverse equation we discussed earlier. Since e and n are co-prime to each other, this can be written as this, which simply means for some value of d, the left hand side and right hand side will be equal to each other or equal to 1. We can either do this using pen and paper, but we don't need that. Let's execute a simple bash command to compute d. If you don't want to execute the command, you can simply execute this little script. It is also included in the GitHub repository of this tool. All we have to do is pass two numbers and it will give modular multiplicative inverse of that if found any. So here the D is 1741. Let me break this command down for you. In the first instruction, using for loop, we are iterating through all the numbers from 1 up to the phi n, and in the next instruction, we expressed it in the mathematical terms that we discussed earlier in modular multiplicative inverse equation. Then we are simply checking whether product of the number from the for loop and e integer modulus operator phi n is equal to 1 or not, since it is necessary, as the whole equation will fit right only if LHS equals to RHS. If we find any number, it will simply give us modular multiplicative inverse, which will be our decryption exponent or integer d. Now in the next step, since we calculated d, the pair of d and combined is our private key. So far we have computed everything that will help us performing encryption and decryption process. Now for the encryption, the equation is this. Here C is ciphertext, P is plaintext, E is encryption exponent, N is PQ product. Now for performing encryption and decryption process on integers, we need to remember one thing. Choosing plaintext such that plaintext is greater than 1 and less than our PQ product, which is N. In the next step, or the decryption process, we have P, which is plaintext, C is ciphertext, D is decryption exponent, and N is product of the two prime numbers we initially chosen. Let's do the encryption first using the script. Let's see if we can decrypt it using our Python script. Now you may think that here we are only encrypting integers, and what if we want to encrypt some textual values such as alphabets or special characters? For such case, the base concept is same. We can encrypt other characters as well, but for that we need to use ASCII values or converted decimal form of the binary encoded values of the characters. For example, ASCII value of letter A will give us an integer value of 97, and we can use that, or we can encode the letter in binary form, and from there we can convert them into decimal form and can perform both operations. Just for the sake of better understanding and simplicity, this script here encrypts the characters based on their ASCII values. For example, the plaintext QWERTY will give us this ciphertext. Since the working of this is based on ASCII values of a character, we can get weird characters in output. Let me just explain how the program is implemented and performs encryption and decryption. So here, these are the corresponding ASCII values of our plaintext. These here are the ASCII values of the encrypted character or ciphertext characters. These numerical values are inserted in the equation in order to find our ciphertext and plaintext. You get the idea, right? Try to solve all these questions. You can use pen and paper, or you can also use the tool we used in this video. The link to download that tool is included in the description box below and also pinned in the comment section down below. Also, do not forget to write your answers in the comment box down below. So that's all for today's video. I hope it has been informative for you and you enjoyed it. If you gained any knowledge from this, do not forget to like this video and subscribe to this channel if you haven't done it yet. We'll meet you again with another cybersecurity or programming related video. Till then, take care and goodbye.